between our forgotten normal vector and our vector field. Now, if f is perpendicular to s, then that angle is going to be 0 or 180 degrees. And we're going to get the full amount of flow through the surface. It's just going to be the field strength multiplied by the area. If, on the other hand, f is perpendicular to the normal vector, then it's parallel to the surface and we get no flow. And if we're in between, well, if you think about it just a little bit, the function that most plausibly solves the question is going to be the cosine of the angle between the normal and the force vector. So the cosine of the angle between f and n is the key. I'm not going to write out all the details of this. It should be obvious to you if you think about it for a second. When f is parallel to n or in the opposite direction, the magnitude of the cosine is 1, so the magnitude of the flow will be the whole flow times the area. If f is perpendicular to n, then the cosine of that angle is 0, and we get 0 flow. And ultimately what we're talking about then is just the flow is simply f dot n delta s divided by the magnitude of n. And the connection is simply that the cosine of theta equals f dot n divided by the magnitude of f times the magnitude of n, so that this expression is simply magnitude of f times cosine theta times delta s. Magnitude of f cosine theta is just the component of f perpendicular to our delta s surface. You actually can't be perpendicular to a surface. You can be parallel to the normal vector. Again, a little abusive language here. But we can then say that this is nothing but f perpendicular times delta s, and it's the magnitude of f perpendicular times delta s, but with plus or minus because of the cosine of theta. And we can worry later about the details of this calculation, but this sketches out how we can calculate the flow over a small surface increment. And this pretty much outlines the process of summing f perpendicular over delta s for all of a surface gives us what we call a surface integral. So we're going to develop the idea of a surface integral in terms very similar to those that we've seen here. If, For example, we want to know how much magnetic field flows into the region bounded by this cup. We can calculate the surface area integral by figuratively subdividing the surface of this cup, the conic surface around the edge, the flat surface around the top, into tiny increments, delta S, with sample points, etc. Calculating the F dot delta S, or F dot N delta S, contributions over all of these surfaces, over all these tiny increments, summing them up to get, again, a surface integral. In this case, we would probably set up two surface integrals, one for the conic region, one for the plane region.